Hello, everyone. Thanks for having me. For me, I'm very elated. It feels like a homecoming for me because I was born just 5 minutes from here. I'm very, very local. There's a lot of friends in the audience that created companies, AI companies. There's my cousin that works in the robotics company here, Lucia. So I'm very happy how this city grew up and beyond the potential that we had. And I would like to tell a little bit of my story. I have only 20 minutes for that and 10 minutes for questions. So I selected some of the things that I worked on for last 3 years. And so in the last 3 years, I try to be actually always inspired by education and actually try to broaden the education that I learn in math seminars of Slovakia to large language models. In Slovakia, we have this, or Czechoslovakia, John Amos Komenský, that was having this paradigm that kids will be more interesting to learn when they will play with each other. And so I try to bring these games to large language models. How to actually teach llamas and Gemini to play with each other to get better and better. Because in a sense, AI is like, growing up the kid. You just don't need to buy them an ice cream or take them to a theater. So what I've been doing in the last 5-6 years, lucky enough that I participated in training models like Gemini or Llama. So if you go to this website and interact with these models, you will actually encounter some of the algorithms that were used to train and fine-tune these models. All right, so I didn't do it by myself only. We have a large set of teams. AI teams are getting bigger and bigger. So there's a lot of my students, my collaborators, both in Google DeepMind, in Meta, my postdocs, my peers in US and in Europe, people that came from DeepMind to Meta with me and from them to the startups. I want to thank them because without them, this would not be possible. And if you want to learn about details, you can ask me during the questions over the coffee break, or you can see some of the related papers that were published or will be published in next month. All right. So what was always my way to approach teaching AI to do things? My view was that we should not spend a lot of time training models before they become useful, because if you have a kid, you don't need to tell them, this is your mother, this is your mother, this is your mother, for a kid to know that's their mother. But oftentimes, large language models actually work like that. We need to give them enormous kinds of data and enormous kinds of labels. And so sometimes in the past, we used to spend so much time labeling the data that it was even wasting our time rather than giving us some extra time to have. And so I approached AI in I started about more than 25 years ago, kind of with two paradigms, two principles. Self-supervised learning, spend as little time as possible to teach the models, and also game playing. Because one of the ways how you can actually improve itself is playing game. Like imagine that like you're learning chess, you're playing with the peers, or you can play sports like tennis in a peers. We actually refer to these sports because they are very good examples how to train language model. But it's actually very important who you play. It's kind of important you play with your sparring partner, with somebody at your level. Because imagine that I want to learn chess and like I pay Kasparov to play with me, or I pay Nadal to actually play on their full potential. I always lose because I'm compared to them, I'm nobody, and so I will not learn anything. It's sometimes better that I actually play with somebody at my level, because sometimes I lose, sometimes I win, so I can make a difference between what works and what not. Because if I play somebody so much better or so much worse than me, then I don't have much time to learn. I can play with my 2-year-old niece, I always win, but it's not something that I can improve on. So let's see how we can actually bring these paradigms, these ideas to large language models. And you probably all know this, review how actually right now the large language models are trained at this time. Or let's say how ChatGPT was trained in the past 2 years. So there's always three three paths. They don't necessarily need to be, but we usually separate them in 3 stages because this is how we separate the teams and often the data. So in the first phase of training, things like ChatGPT, Gemini, and Kimi, DeepSeek, and whatnot, you learn our internet. So you scrape on internet, you crawl the web. Sometimes you pay for extra data. If you have a company who may be using your own private data. And what you do, you try to predict the next word. So you put a sentence and ask, what's the next word? If it doesn't do well, you penalize it and try to improve it next time. So after this stage, you have something, that's called pre-trained model or based model. And what it can do, well, it can do what you thought it. It can complete the sentences. It can say that, like you could start a sentence, it's continuous. It's like a chatterbox. It's blah, 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 blah. It's not a conversation. It just, it finishes the book. It completes the text. So for AI to be useful for us, we would like to make it do stuff for us. And so we put the phase that we call like supervised fine-tuning or instruction fine-tuning. We want it to summarize the text. We want it to respond to a request. So we change the data now, and we fine-tune. We change the weight just a little bit, and the input is now different. Input is some prompt and what we would like to have an answer. So we say, like, what's the capital of Slovakia? It's Košice. Or it would give me 3 colors, and we want to make sure that there are 3 colors, not 4 and not 2. And so we give a lot of these sentences. Oftentimes, we have to pay people to give those, give those answers, or actually give the pair. So, input and output is slightly different, but the training is almost the same. But at this time, models can become conversational because, they output sentence and wait for the answer back. So we can now start to have a conversation. They follow our instruction. It's the beginning of models being useful for us, because before it was just completing the sentences. And the third phase, where I spend most of my time in, it's called reinforcement learning. Because at that phase that we call supervised fine-tuning checkpoint, the model saw internet and can respond to our questions, but internet is really, really nasty place, right? Like, so if you look at some discussion on Facebook or newspapers, for example, in Slovakia, people are not nice to each other, and the networks, get this data in. And so, when you ask the question after his face, usually what you get, it's some slur or some vulgarism just after that. And oftentimes, big companies don't want to have these things, right? Like, you also don't want models to be sexist, racist. You don't want them to give you financial advice. You don't want them to pretend be a doctor or anything like that, right? Like, you want to be useful just for the cases that were useful. And then also, you want to improve their capabilities, because here, you only gave pairs of input and output, but you would like the model to go beyond that, to give you something more that were not taught, right? Like humans can. Humans can do more than they just received. But let's see where we are with this training. Reinforcement learning, which is the methods that we used in the last part, we're used to train things like, chess, AlphaGo, StarCraft, Atari games, 10 years ago, and that was some of the first successes, in the company that I work for, DeepMind, right? But imagine how it was before. The network was very small, but we did a lot of trainings, reinforcement learning trainings, like 10 to the 10. And at the end, we have a Mario brother that would just go and jump up, and collect some strawberries. Now we have models like Llama 3, that I trained was 4 or 5 billion parameters. We only do thousands, sometimes less, training steps, and we're hoping that it will learn something more. So we need to be really careful, which steps we do, because we don't do that many. So we need to decide them well. And so there is a kind of the paradigm that it is done to actually learn how to actually teach those models what to do well. So in last phase that we do, that we actually collect feedback in a different way. We take the model from this side, which is supervised fine-tuning feedback. So we ask a prompt, what is the capital of Slovakia or Slovakia? We sample multiple answers because answers from models are stochastic, and we have multiple answers, and we ask humans, which one do you prefer? And of course, it should be correct one, but there's also ones that doesn't insult you, doesn't pretend to be somebody else, and they have a comparison. So the data comes in a very different way. Data comes in a way that input, potential outputs, and humans choose is which preference do you have, right? And so in the big tech companies, we paid hundreds of millions to people that will decide which of the two answers to prefer. It's a huge market. There is companies, pitching to me every week. They have a different way of collecting answers. And even with hundreds of millions of dollars, this is not enough. Because there's so many comparisons we would like to make between. So what we usually do at this stage, we actually train the model. So we have this prompt, like question, the answer, and we try to actually learn how would the random human respond. And so what we do, we convert them to the ELO score. ELO score is something that every chess player has an ELO score, or for those of you who like sports, maybe you know ATP in tennis. This is exactly what it is. For each of the answer or pair question answer, we have a number. And so that's a number we can compare how good the answers are. So once we learn how to predict those numbers without asking humans, then we kind of don't need humans anymore. And we create these ELO scores. And then we said, okay, well, we pay 100 million to humans to learn how humans would rate the answers. And then we use it. And so I spent and this is how ChatGPT is trained. And so I spent my last 3 years of my life kind of showing that this is wrong and we could do better. And I'm going to spend next 8 minutes to convince you that there is a better way to do it. So instead of actually taking this ELO score, we will do something slightly. So we will not learn like chess ELO score, but we learn something we'll call preference model with the same data. So the data is always input and potential output. And we put inside the prompt X, so the question X, answer, potential other answer, and we output, how do average human would prefer answer with these others, right? On this question, what is capital of city? Is the answer Bratislava better than answer Košice? And now we'll try to convince that the second place is better. But what we will do with this model? So back to intuition, ChatGPT is trained this way. Well, we train this pre-trained model, then we fine-tune it to actually teach us that it's conversational, so we can have conversation. At the end, we do this last step we're talking about. And how we do the last steps, we take the checkpoint, the set of weights, and we ask these humans, or the model that we replace the humans, say, find me one other model that is better than this. So if I would play the game, back to gamification, I want to find a model that this person would win if you play a chess game. Here, the game is different. Here, the game is, I give you prompt, a question to chatbot, and the game is who gives the better answer. This is the game. Who gives better answer wins. And the ChatGPT starts with one model and finds another model that would win against this model, right? Which is very reasonable. I want to improve. I want to find my model that's better. But I thought that's actually not good enough. I have one model that beats this one. But if this model is just my little niece of 2 years old, it's very easy to win, and I'm actually not very good. I don't want just one model that beats one other model. I want one model to beat them all. So I would like to have something, that's if you compare it to every other thing, it's better. So there's nothing wrong with ChatGPT way of training, but it's just not enough. We can do better. And the better is that I want to, at the end of training, have model that if I compare it to any other model, it wins. And this is not a new concept. This came from John Nash equilibrium. Like, I want to have a models, keep training, keep playing with each other, at the equilibrium. If I compare one model with every other one, it always wins on expectation. And so I would like to now say why this way of training model is better. And so one is this diversity. Not to go to politics of Slovakia, let's take American. In the US, you have Republicans and Democrats, right? If your data is half Republican and half Democrat, and you just have, for example, one data point, bless you, a Republican, then everything will be Republican because this previous way of training is winner takes it all. And this is even an extreme example. Let's say you have 100 minorities, and one minority is slightly bigger, then the model will only prefer this minority. And since this isn't good, we would like to have models that have opinions proportional, right? And so this is not possible with this model, with this previous model, but it's possible with this Nash equilibrium. And it's also very brittle because imagine you have a little bit more data of Republican, and now I just get 2 data points on Democrat. Now Democratic prevails, and now everything changes, and all the model is Democrat. It's not stable. It's not very good for production that can model completely change. Another thing is that, it's not very good for modeling human preferences because ELO score actually can rate every single person by the score, in chess or in tennis. But like in tennis could also happen, that I'm better than Lucia is better than Juraj, and Juraj is better than me because we know how to, take advantage of our slight mistakes. And so it's like a triangle. This could happen, but the models, like the ELO score model or ATP in tennis, doesn't actually, there's no way you can satisfy because every single thing is just a number. And so our way actually is, for us, it's totally possible to have these kind of circles that's, somebody's better than somebody else, better than third person is better than me, or any other circles. The third one, and I will not go to details, I promise, of these equations, but I'll explain it. So imagine that I play chess, and I am the second worst chess player in the world, right? And imagine that the mayor of the city is even worse chess player. I don't know that, right? And so, but if I only play with the mayor of the city, I will win all the time because, but I'm also really, really bad. And so, but I can make my ELO score, my chess score, the high possibly because I won in all the parties, all the plays that we do. But this would not happen in real life. I mean, this could happen in real life. But, if I will claim that I have the highest ELO score in the world, they will make me play with somebody like Kasparov and I would lose, right? But, I'm very insecure, so I only play when I can win. This is not a random example, because when we ask humans then to compare to outputs of the model, we only give them one comparison. And so we don't know, whether this comparison compares to something else. So another example, imagine, here we are 2 halls, right? Here, let's say we all play with each other and we know who is good. And they play with each other and know who is good. But between the 2 lecture rooms, nobody play with each other. So maybe it's the case that person with the highest score here is even worse than the person with lowest score there. And so that's a problem. It's actually in ELO score, the way how you collect data really matters. While in our way, it does not matter. Because if I play with the mayor of the city, the only thing should happen is just confidence intervals, how good we are, and it should not affect the scores of the others. But the way that ChatGPT trained, every single place affects everything others, and this is not good because it's not related. But none of these, nice and mathematical formulation convince Sundar and Demis and Mark to actually implement stuff. They only care about data and the results. So we actually did the simple machine learning model. So we took all the preferences we collected with the humans. We trained the model one way. We trained the model the other way. And said, can we predict what human thinks? And the model trained the way that I'm describing one. And that convinced them to apply these techniques to the training. So now that I hopefully convinced you that this technique is better, the question is, how do we actually train it? And I spent 10 years to find this answer. This was a question about the games and trees, and it's very similar to the way that AlphaGo and chess are trained, but it had to have some new things. The thing is that how AlphaGo and chess are trained is that we build trees, like I play something, Juraj plays something, I play something, and at the end, somebody wins. And so we built trees like that. So this is, trees of the game called Go. And, has a lot of potential states, potential options we can play. But to the games that are even bigger, like in a language, like imagine for every word, we have every other possible word, we have all the possible word. There's actually infinite option. There is no way we can draw this tree in a memory of computer because it's just too big. But the way how we actually train the models this way, are very different. The one thing that we know in AI in last 15 years is how to make this big distributed training. So we buy a lot of GPUs, the clusters like Perun and Devona. We put them there. They do inference. Let's say they play the games like Go, or they output the sentences to the phrases, and they put the answers to something we call replay buffer, like a database. And then we have a, let's say, very simple CPU computer that takes few of the answers, improves the model, and then distributes the policy. And this is kind of very simple, but it's all synchronic. But since we have hundreds of thousands, maybe a little less here, GPUs, then enables us to scale. But we cannot ever represent the tree. And so we know how to do this way. And so it was open question, how to actually solve these games that we cannot do the trees and find the Nash equilibrium with those games. And so, I started working on it actually with another person from Košice on this problem in 2014. And we solved problem in 2014, and we call it implicit exploration. And it was actually very simple. We had some, I will not go to details, but we have some kind of fraction, and we just added small number. And almost all my research was like adding some small numbers to the fraction for different reasons. So if I ever die, you say that all my contribution to science was just adding some small number to the fraction. You can put them on the grave, if when I die, please do. And so there were a lot of people that follow up from our work, and we came back to it in 2021 when he almost for his first algorithm that doesn't draw the tree, but it was not optimal. Other people from Berkeley continued, but it was not optimal, and we got back to work. And so the thing is that you actually kind of need to know the full tree to be optimal. But we had this idea, well, if the opponent at the Nash equilibrium is optimal, he or she needs to know the tree. So if you observe our opponent, so it's pretending it's us, we can actually guess what the tree is. Not fully know, but it guess. And that helped us to solve the problem, and we claim the success. And we apply these things to training large language models. We call it Nash learning because of the John Nash that received a lot of prizes. And there's still very important concepts in economy and finance that deal from it. So the final thing is quite simple because only simple things work. The algorithm, even if it looks very maybe complicated, it's only one line of code at the end because only these things scale. At the first time you train this preference model on the outputs of humans, which kind of ice cream or which kind of answers you prefer. You train the preference model, and in second phase, you find this Nash equilibrium using the open problem we tried to solve for 10 years and got the best paper award 2 years ago. I don't have much question to the details, but already I can kind of explain how this works. So, we could also not do anything and just use algorithm from John Nash. So what John Nash did is that you want to find a model that's better than all of them. The first step is find one model is better than this one. So it's like what ChatGPT. So John Nash actually invented ChatGPT in the 60s, but not knowing about it. But he didn't stop there. He said, you find something better than this model, take these two models together and find something better than this one. Then take all three together and find something better than three of them until you cannot improve. And so there's nothing wrong with this algorithm. The only issue that all the different models, beginning, ChatGPT 1, something better, they are huge, 500 billion parameters, so it doesn't fit. And so that's the issue that we had to solve, kind of being able to represent all the models without fitting them in the memory. So based on some algorithm of Arkady Nemirovsky from Russia, we bring algorithm called Nash mirror descent the way how we can actually represent all the models. So I have a few seconds to see how the algorithms work. So you start something, you start with one model, you find something that's better than this one. This is ChatGPT. You cannot really save them all, so you kind of combine them. You say like, I put like 50% of this and 50% of this one. I average them, so I have only one, and I found better than its average. Improves, I have some improvement. I average improvement with something that I had, I improve, and so somehow averaging this model represents all the others, and I keep improving until I get something that I cannot improve. And this is what gets us the result. And of course, like the guarantees, the heads of deep minds or Meta don't care. They only care about if it does better than the all. And in this final table, you can actually see like all possible way of training algorithms, and then you compare how much humans would prefer, this one to this one, right? So if you compare yourself to yourself, it's 50%. Look what ChatGPT does. ChatGPT, if you compare it to what it starts from, 99% prefer ChatGPT than what was it before. And if I take our way is, for example, this column, it's only 98. I said, oh, you are worse. But if you compare ChatGPT, this is RLHF, to other models, sometimes it's better, sometimes win, sometimes worse, sometimes 40%. You need to be under 50, above 50 to be better, right? So sometimes better, sometimes worse, because we was only trained to beat one model. It's like I was only trained to beat my, in chess, my 2-year-old niece. While if you look at it's not biggest number, but it's always better than 50%, which means if you compare our model to something else, it always wins. And so this is the way how we actually brought the games to a large language model, and this is what now you can take advantage of the current generation of models. Thank you very much.
Dámy a páni, Michal Valko. Michal, čísla a rovnice nikdy nevyzerali viacej cool, ako keď si ich prezentoval ty. Mám pre teba, môžeme poslať Q&A? Super. Mám pre teba jednu otázočku. Môžeme sa dostať do bodu, kedy prestaneme rozumieť, ako sa tieto veľké jazykové modely učia?
To sa môžeme, keď ich necháme akože... Teraz veľa ľudí programuje tak, že vlastne nechá veľký jazykový model doplniť niečo a môžeme sa dostať do bodu, že tomu nebudeme rozumieť. Čo je veľmi riskantný mod, lebo nevieme, čo sa môže stať. A práve preto by sme aj napriek tomu, že vlastne veľké jazykové modely môžu za nás robiť nejakú prácu, my sme stále mali mať nejaký dozor a rozumieť, čo je za tým, aby sme to mohli zlepšiť a lepšie kontrolovať. Môžeme sa staviť, ale podľa mňa by vždy mala byť niekto, kto tomu rozumie. Presne tak, ako je to s autami. Ja neviem, ako auta sa vyrábajú, ale viem ich používať, ale viem, že niekto to vie a že mu môžem dôverovať, že si do toho auta môžem sadnúť. Tak presne tak myslím, že by mal byť prístup aj v týchto veľkých jazykových modeloch.
Michal, čo je hlavná limitácia alebo hlavné limitácie pri ďalšom vývoji veľkých modelov a AI?
Jedna z limitácií, že vlastne tieto jazykové modely, ktoré máme, sú vlastne ako keby taká veľká sumarizácia textu. Je, že to vlastne taký Google vyhľadávač, ale kde videl celý internet. Vlastne ľudstvo je veľmi dobré sumarizovanie informácie. Takto ako ľudstvo sme akože pokročili veľmi ďaleko, keď sme si vedeli vymieňať informácie, keď sme mali Gutenbergovú časť, keď mali internet. Teraz vlastne máme takú tú encyklopédiu na steroidoch a proste niekto, kto nám ho poradí. V tomto sme ako ľudia dobrí a môžeme debatovať, ako sú veľké jazykové modely, sú dobré. Ale sú celkom na úrovni. V čom sú úplne zlé a ľudia sú stále úžasní, je ako vieme rozhodovať v čase neurčitosti. Keď si poviem, že ako sa mám dostať z Košíc do Bratislavy, tak sa môžem spýtať 5 ľudí a budem mať veľmi dobrý prehľad, že niekto od Bratislavy dnes prišiel, niekto pozná tú cestu cez Budapešť, niekto vie, kedy bude Smartwing Slovakia. A ja si viem povedať, že ako je šanca, že sa do tej Bratislavy dostanem. Veľké jazykové modely nevedia, čo nevedia. Akože oni sú stále o niečom veľmi isté. Lebo môžeme sa spýtať, akože model si myslí niečo, a si povedal, že si istý, ja si myslím, že naopak. Prepáč, je to naozaj naopak. Ten model môže povedať toto alebo opačne, ale stále je si istý, že je to pravda. toto my vieme, keď sa ma spýtaš otázku o kvantovej fyzike, o ktorej nič neviem, môžem ti povedať náhodnú odpoveď, ale zároveň ti poviem, že vôbec nie som si istý. Toto je veľmi ťažké a toto je veľmi najväčšia výzva a limitácia. V tomto je ľudstvo úžasné a v tomto sú modely v podstate úplne na nič zatiaľ. A toto je tá budúcnosť, ktorej by som chcel byť súčasťou. Spraviť to tak, aby aj tie modely sa vedeli rozhodovať s touto neurčitosťou.
Úžasné. Michal, veľká vďaka. Ešte raz veľkánsky potlesk pre Michala Valka. Ďakujem.